Hello again. We are now ready to talk about the equations used in slope stability analysis, and we're going to look at a really common, very powerful approach called the limit equilibrium procedure. Before we do that, it's worthy to note that there are other ways to do slope stability analysis, and so let's look at a couple of other techniques before we dive into the details of the limit equilibrium method, one of which is a map-based probabilistic analysis, and this is kind of a GIS or geographic information system geospatial analysis approach. And in this case, you generate geospatial data describing the soil type, the soil strength parameters spatially, the slope, the moisture content, slope of the ground, obviously. Sometimes vegetation is included. And then, using an algorithm, you could probably employ some kind of machine learning to help with this. I haven't seen that done, but I'm sure people have tried that. And basically, you come up with a probability of failure, so it's not a very precise way to analyze a slope. It's more a way to highlight areas that would be more prone to landslides and slope failures. It's just a broad mapping technique. Another technique which is becoming more and more popular, and there are actually a fair number of tools to do this, is a deformation analysis. So in this case, you would do, typically this is a finite element method, often a three-dimensional finite element method, where you put in the geometry of the slope and its soil properties, it is the material properties for the elements. And then, based on the weights and the pore pressures and the stresses involved, it looks at the stress-strain relationships along certain areas where the shear stress is high, as shown in some of these figures, and then it comes up with a factor of safety against failure. And so this is what you do when the stakes are high and you need to do a really sophisticated analysis. But in many cases, the limit equilibrium method is the method of choice because it's fairly simple, and you can do it very quickly, especially with the aid of modern slope stability software. And given the levels of uncertainty we have on strength parameters, it's generally considered to be sufficiently accurate. So how does it work? These are the main steps involved with the limit equilibrium method. First of all, you select a candidate failure surface. So going back to something like this, you would say, without the aid of a finite element analysis, you would just pick, say, a circular surface here, and you would say, I want to calculate the factor of safety for that circular surface. And then you would repeat this multiple times until you find a failure surface that has the minimum factor of safety. But let's say, for example, you pick a surface that kind of corresponds to this shape. Then you calculate the stresses along that failure surface, assuming that the soil is at the limit of static equilibrium. So what forces are necessary, what shear stress is necessary along that surface to hold it in place? And that's a function of the geometry of the surface and the soil above it. It's a function of the weight of the soil above it, and you basically do kind of like a free body diagram. You look at moment equilibrium, force equilibrium, say, okay, what would it take to hold that in place? And then you look at how much shear strength is available along that surface, using the properties of the soil. What cohesion do we have? What is the friction angle? And then You take that strength divided by the stresses necessary to keep it in equilibrium, and that's a factor of safety. So, for example, let's suppose that the strength you calculate along that surface is 1.5 times larger than the stress required just to keep it in equilibrium. Then we would say it has a factor of safety of 1.5. We've got a reserve there. Or in another case, maybe the the strength along that surface is only 90% of the stress required to keep it in equilibrium. Then the factor of safety is 0.9. So any factor of safety less than 0 means the slope would likely fail along that surface, and a factor of safety greater than 1 would mean it would likely be stable. Now, in design, you typically want a factor of safety of at least 1.2, preferably 1.5, something like that. The higher the better. But often when you're designing a slope, you're deciding how steeply you can cut a slope. So let's say for an embankment next to a highway or a cut or a fill area, then you want to... Sometimes the decision of what slope angle you use can make the difference of millions of dollars, and so you want to analyze it very carefully. So let's suppose I mentioned before that you select a candidate surface. You calculate the factor of safety for that surface, and then you select another surface and you do it again, and you keep doing it, and you try more and more surfaces, just a really large number of different shapes of failure surfaces through the slope, and until you feel like you've adequately explored most of the available options, and then the surface with the minimum factor of safety is called the critical failure surface, and that's the factor of safety you use in design. Now, this requires a lot of computations, but fortunately they're very easily automated in slope stability software, and the whole analysis process can often be done in less than a second to explore dozens if not hundreds of failure surfaces and calculate the factor of safety. So the process is more just setting it up and then pushing a button to calculate that factor of safety. We're also going to look at a number of different solution techniques in addition to the software as we go through this semester, some of which you can do in a spreadsheet pretty easily. Now, this process of doing this analysis, let me jump back a little bit. When we look at these candidate surfaces, I mentioned a circular surface or a near circular surface in my example. That's probably the most common failure surface we assume, and as you saw in our earlier video, a lot of the natural slides they kind of rotate along a curved or circular failure surface. But sometimes you have a planar surface. If there's like a weak layer course parallel to or along a straight line, this can happen. And then sometimes you have like a weak seam somewhere like this, and then you can do a non-circular failure surface may end up getting you a more critical factor of safety than a circular surface. So when we get into using our slope stability software, we're going to look at both circular and non-circular failure surfaces and how to do a critical search for a factor of safety using the limit equilibrium method. Now, the factor of safety, another thing about the factor of safety, as I mentioned, it's the soil strength divided by the shear stress necessary for equilibrium. If you solve that for the shear stress necessary for equilibrium, you have the strength divided by the factor of safety, or C plus sigma tan phi divided by the factor of safety. So you can think of this as the stress holding it in equilibrium can be thought of as the available strength divided by some factor of safeties. You're using some portion of the available strength. For example, let's say the factor of safety is 2. It would be the current shear stress necessary to hold an equilibrium is basically 1/2 of the available shear strength. So if we divide both the C and the sigma tan phi part, C over the factor of safety, that's sometimes designated as C sub D, which is the developed or mobilized cohesion, and tan phi over the factor of safety, we often write that as tan phi D, the developed friction. And a lot of our derivations of equations related to limit equilibrium method, you'll see this developed cohesion and developed friction as a way to represent for both the cohesion and the friction the portion of that that's currently mobilized to keep the slope stable. Another thing that's I mentioned that when we calculate the stresses along the failure surface, we have to ensure that static equilibrium is satisfied. And so we end up looking at, we sum the forces in the x direction, we sum the forces in the y direction, we sum our moments, and we often break the slope up into smaller individual parts. And for each part, we sum the forces in the x and y and direction and moments. And we end up with a big number of equations. And typically, the number of equations we have is less than the number of unknowns. And therefore, if the number of equations is less than the number of unknowns, we have to apply some simplifying assumptions. And there are certain techniques which we'll see a little bit later in some of our videos that satisfy all 3 conditions, and some satisfy just a subset. For example, there are some limit equilibrium methods that only satisfy moment equilibrium. They don't satisfy force equilibrium. There's also a class of there's a limit equilibrium method that only satisfies force equilibrium. It doesn't do moment equilibrium. And there are a few methods that satisfy all 3, and we call those complete equilibrium methods. And we'll explore some of those as well.